Okay, I think our numbers have stabilized. So welcome to our February meeting at the RASC Ottawa Centre. Special welcome to other RASC centers and folks that are visiting with us for the first time. We are on Zoom. We're on Zoom webinar. We are recording this session. Rest assured, those of you who are not presenters will not appear in our recording, but your chat will appear. Please use the Q&A box at the bottom of the screen to ask any questions to our presenters. We will not be monitoring the chat box. And just a reminder that your chat box comments can be seen by all. Raise hand is disabled, so if you need to get our attention, please use the Q&A box. I will be reading out the Q&A questions to the presenter so that it is recorded in the video. So here is tonight's program. We've got our introduction, Ottawa Skies. We've got our guest presenter, Michael Stewart from York University, presenting on resident space objects. Andrea is going to be doing observing Mars clouds. Richard Taylor is doing a thing on plate solving. We're going to have a break. Then we got the RASC Robotic Telescope observation reports and our monthly observation challenges put together by Oscar and any last minute announcements. Welcome to our new members. So you can see that our presenter tonight, Michael Stewart, is one of our new members. So welcome, Michael, and welcome to all the others. We've had 14 new members in 2023. Members in the news, Jim Thompson. So Jim Thompson has received the AstroImager Solar System Certificate and the AstroImager Wild Field Certificate. So congratulations, Jim, for those awards. We had some unfortunate news. On February the 1st, we lost one of our preeminent Canadian astronomers, Terence Dickinson. Many of us own his books. He was fascinated with astronomy at age 5. He co-founded Sky News, and he's received several national and international awards, including the Order of Canada. And he also received some honorary doctorates from Queen's University and Trent University in Peterborough. So we pause and think about him and his passing and his contribution to the Canadian astronomy work. Okay, Chris, we'll move on. So we always encourage folks to join the Royal Astronomical Society. A regular membership is $103. Family membership is $97.50, and then $16.90 per adult and $9.20 per youth. And if you are a student or under the 21 years old, we have a youth membership for $62.40. So what do you get with this membership? Well, locally, we have the Ted Bean Loan Library, so we have a number of telescopes that you're welcome to sign out and use. And we just have a brand new loan librarian, and I'll be mentioning him in my President's Report in the upcoming Astro News. Once we get back into the Canadian Aviation and Space Museum, and hopefully that's going to be soon, we have our Stan Mott Library. And we also have the Fred Lossing Observatory out near Almont, and it's an excellent facility, and I encourage members to take advantage of that. From a national perspective, you get the Sky News magazine, which comes out every couple of months. The journal comes out every couple of months as well. You'll receive your Observer's Handbook. You normally get it in December the year before. And monthly, we have Gordon Webster puts together Astronauts, articles from the folks in our local center here. An excellent publication. It is an electronic publication. And one of the biggest membership benefits are all the people. And I encourage you, whenever we get together in person, to come out and meet some of the members of the RASC Ottawa Centre. And yeah, hopefully it's a little tough at this time of year. Once we do start meeting back in the museum, we'll be able to to meet in person much easier. So Ottawa skies for February. What's happening up in the skies? Well, let's take a look at the moon phases. So the full moon is on February the 5th. We got a new moon on February the 20th. And the full moon this month is known by our Indigenous folks as the snow moon or the hunger moon. It's difficult to hunt at this time of year. As you can see, the days are getting much longer. So I certainly noticed in the evenings that it's staying brighter that much longer. And I just saw a chat pop up there. Somebody's asking if the meetings are permanently online. They will continue online. Even once we meet back in person, we will have a blended format. Thank you for the question. Mercury is not visible. It's rising and setting with the sun. Venus is visible after sunset. I've seen it up in the evening sky the last little while. Mars is visible in the evening. Jupiter is visible in the early evening. It's setting earlier and earlier. Eventually, we won't be able to see Jupiter for a while. Saturn's visible at sunset, first half of the month. Uranus is visible in the evening, and Neptune is visible in the early evening, first half of the month, after which it rises and sets with the sun. I bet you that's how some of us feel this month with all the clouds. So patiently waiting for clear skies. So thank you, folks. So welcome to Michael Stewart. He's currently an Earth and Space Science Master student at York University, where he measures resident space objects. So I'll let Michael introduce you to this fascinating topic, and we're just going to take a second here while he switches to take control of the slides. Welcome, Michael.
Hello, nice to be here.
Okay, I'll get you to start your video if you could.
Yep. Give me 1 second.
There we go. Okay, I can't highlight you if you were spotlight. There you go. Now you're spotlighted.
Oh. And am I sharing the screen?
Yeah, that looks good.
Perfect. Okay, so today I'm going to be talking about, I guess my name is Michael. I'm a master's student at York University, focusing on measuring resident space objects, both photometrically and astrometrically. Today I'm going to be talking about some of the research that I've been doing over the past year. Primarily, I've been using Python for resident space object photometry. So I'll talk a little bit about sidereal stair mode photometry and how that relates to absolute all-sky photometry of resident space objects. I'll talk about track rate mode photometry and the possibilities of using both absolute photometry on those images and performing differential photometry as well. If I have time, I'll talk a little bit about astrometry and with a conclusion and discussion, answer some questions if anyone has those. So first off, what is a resident space object? Well, resident space object is defined as an artificial object that orbits around another body. This could refer to both satellites or space debris. With more and more satellites entering orbit, it's important to maintain the current database for collision avoidance and general longevity of spacecraft. By using photometric methods on satellites, their apparent magnitude can be used to produce light curves, which can then be used to characterize the satellite by bus type and attitude. You can determine the attitude of certain spacecraft from this. Additionally, the astrometric measurements, the rate ascension and declination of resident space objects are important for orbit determination. So to start off with, let's look at sidereal stair mode photometry. Now, what I use AstroPy. AstroPy has a lot of great packages, great libraries within it for performing photometry. One of those is PhotoUtils. And so to start off the photometry process, of course, you want to subtract your bias frames and dark frames and divide by your flat frames if you have those. You can use the CCD-proc package within AstroPy for that. But after that, we can use the PhotoUtils package. And this is where I start the slides here. On the top left, you have a sidereal stair mode image, and you estimate the background, and then you subtract that background from the image to produce a background subtracted image. It makes it easier to detect your light sources. This is just a picture of the star field SA23. So these are all stars in this image. Now Python does use a bunch of source detection and extraction methods. There is the source extractor package for Python, also known as SEP. And then it also has an implementation of the IRAS star find algorithm to detect stars. And it has its own. So Python Thought Utils has its own detection method called detect sources. And so these just show different ways to detect the sources and extract them. Of course, what we want to do is we want to find the optimal radius of our apertures when we're performing aperture photometry. And so to do this, all you really do, all that I do, I don't know if it's right or wrong, is I calculate the signal to noise ratio of the stars in an image with different apertures, aperture radii. And then I try to find the one that maximizes the signal to noise ratio for a given image. We then correct that aperture magnitude using the asymptotic magnitude from increasing our apertures from 1 pixel radii to like infinite radii. We calculate the asymptotic magnitude and we find this correction value. This will give us our instrumental magnitudes from our sources in our image. So once we have our centroids of all of our light sources, which is like the middle of the stars in this case, along with the instrumental magnitude, what we can do is we can perform plate solving. And so AstroPy has an AstroQuery function that will take these centroids and send these points off to nova.astrometry.net. Nova.astrometry.net will give back what's called world coordinate system information, which matches the pixel locations to the right ascension and declination. On the left here, there is an image of a simulated image that's produced after the image that we imported has been plate solved, the WCS information extracted, and then this WCS information is used to simulate an image. It's just to visually double check that we've solved it correctly. So we have the images of the stars, we have the instrumental magnitude, we have the right ascension and declination. The next step for performing photometry, at least calibrating photometry, we need to match these stars up to their catalog magnitudes, their visual magnitudes, visual filter magnitudes, and their blue filter magnitudes. So to do this, again, we use AstroQuery to query the Vizier service. We have the field of view of the image, the world coordinate system, from the world coordinate system information. We have the field of view. And so we just take this field of view along with the center of the image, its right ascension and declination center, query that region in the sky to get back a catalog. Typically we want to use the APAS catalog, which is found within the UCAC4 catalog. That's kind of like a sub catalog. And this APAS is just photometric stars. So it has well-known values for the stars in the visual filter and the blue filter. So all this to say, we match the stars up. We have the images of the stars. We have the right ascension and declination. We have the instrumental magnitudes. And now we have the apparent magnitudes. What we do is we need to apply these values to this absolute photometry equation to find our photometric coefficients, our extinction coefficient and our transform coefficient, as well as our 0 point. This will allow us to take any instrumental magnitude, any instrumental magnitude of an object and convert it to an apparent magnitude in a standard system. So the transform coefficient converts our different color filters to a standard system. There's two different standard color filter systems. There's the Johnson-Cousin filters and the Sloan Digital Sky Survey filters. And these transform coefficients can be produced by taking our apparent magnitude from our catalog, subtracting the instrumental magnitude and plotting it against the apparent color index. A linear least squares fit can be plotted against this data to find the slope, and that's our transform coefficient for our specific filter use. On our left is the blue filter transformation that I found, and on the right is the visual filter transformation. And so the filters that you use probably aren't perfect Sloan filters, or they probably aren't perfect Johnson-Cousin filters. In my case, I use ZWO filters. And so these ZWO filters, using these coefficients, they transform the magnitudes into the Johnson-Cousin filters. Right, the next step is the extinction coefficient. The extinction coefficient, your light that's received from a star or any object diminishes as you get closer to the horizon. And so this extinction coefficient calibrates for that. To find the extinction coefficient, you need to take images of a particular star field. In our case, we took images of a SA28 star field at different air masses. You need a big enough air mass difference. And you find the extinction coefficients by, again, using a linear least squares plot against the apparent color index minus instrumental, the apparent magnitude minus instrumental magnitude. This will also result in your 0 point value, which is another coefficient that you need. The last coefficient that you need is the apparent color index. That's found by plotting your instrumental color index against your apparent color index. That gives an approximation of what your color index is going to be for any object. Right, so resonant space object track rate mode. How do you track these satellites of interest, the space debris of interest? What's something that you need to consider? Well, one of the foremost things to consider is that your catalog star density varies throughout the night. As you probably know, the galactic plane has a lot of stars, and it has a lot of catalog values for stars, but not all the time are you going to capture a high density of stars in the background of your image. In two observation runs that I did, one of them, the Anik F1 observation run, it passed through a high density of stars, and the other one, it didn't really have a lot of stars in the background, so it couldn't be plate solved that well, and you couldn't perform differential photometry. So keeping this in mind, it's important to schedule your observations of satellites if you ever want to observe satellites and see where they are in the celestial sphere. To track the resonant space objects, I used SkyTrack, which it's a Canadian-made program. All you do is you have to input a TLE. TLEs define a satellite. You input a TLE or multiple TLEs into the program, and it will. It's compatible with all ASCOM mounts, at least the majority of them, I think. And so it will track the satellites throughout the night. It depends on how fast your scope can track, but sometimes, especially for geostationary objects, it's pretty good because the azimuth and elevation is pretty much the same for geostationary objects. So this produces, when you're tracking these satellites, this produces images like you see here, where the satellites will appear as dots while the stars appear as streaks. And so I've tried two different algorithms, the source extractor package for Python and the FOTUtils, the text sources with a source catalog module. And I was able to find some really good detections, some really good fits for both our stars and satellites. So then from here on, you can kind of label the satellites and sort of try to track them throughout a series of images that you capture, using the same theories that I talked about earlier with the cellular stereo mode, where you apply an aperture correction. You can get an instrumental magnitude of these satellites. And so this graph shows your instrumental magnitudes during that observation run. This is the blue filter, and the next image here is of the green or visual filter versus time. You can then apply the absolute photometry equation with the coefficients that we found to get the apparent magnitude versus time. And as you might have noticed, you go from an instrumental magnitude of -9 to 11-ish, which is a lot more accurate because Yeah, your magnitude of the satellite isn't going to be that bright, at least for geostationary objects. So you can perform that. You can also perform differential photometry, and this is what I've done with ANIC F1. As you may recall, it passes through a high density of stars, of catalog stars. So not only can you plate solve these images that are produced, these streaks. You can take the centroids of these streaks and plate solve them. Not only can you do that, but you can try to match them up with your catalog stars as well, and get some coefficients. Some people say that differential photometry is better. Now, when you're using track rate mode, it can be very finicky because sometimes you'll capture, the program will tell you that there's multiple streaks when there's only one star streak. And that's where you can apply a match filter to the image with convolution. And you can perform all these optimization things to try to get a better result. But at the end of the day, hopefully at the end of the day, you get some WCS information out of that with the plate solve. And this will tell you exactly where the satellite is within the sky, the right ascension and declination, and matching the stars up again. Like I said, you can get transform coefficients. You wouldn't want to find extinction coefficients because with geostationary objects, just because the air mass doesn't change that much, it has a relatively similar azimuth and elevation throughout a given night. So you can calculate the transform coefficients and the apparent color index and apply these to this equation here. Essentially, this is very similar to the absolute photometry equation, but it's different in a differential form. This converts your instrumental magnitude of your resonance-based objects into an apparent magnitude. So we have our instrumental magnitude light curve here, plotted against time. Values are negative 7.8 and 7.5 for the visual filter. And then we transform them into an apparent magnitude. One thing that I noticed was a bit of an issue was these error bars. They're quite large because we don't have a lot of stars in the background of the image. So this causes some probability margins, some big probability margins. I have a little bit more time, so I'm going to touch upon astrometry, which is taking your WCS information of your satellite and doing stuff with that, pretty much. So here's a composite image of where the satellite was recorded, and it's got a backdrop of the night sky. So you can see that there's, I don't know, maybe 24 line of sight vectors of the satellite. Now, what you can do with this is, if it's an unknown object, you can perform initial orbit determination from this and figure out, just figure out where the object's going, what it's doing, all that sort of stuff. But for the majority of cases, we don't want to perform initial orbit determination. A lot of these satellites are recorded. So something that we can do is I've mentioned this earlier, there's two-line elements which define a satellite. We can propagate the satellite with these two-line elements, which is what I've done here. And we can compare that predicted value to our measured value. And so I used a module called SkyField to predict the locations of the satellite with an SPG4 propagator. And this next image shows measured positions of the satellite against the predicted positions of the satellite. So you can, from this information, if you correct it, you can actually correct an orbit that I don't know, NASA maybe made and spit out a TLE for. So that's something that I'm going to be working on for the next year, is orbital correction. So in summary, photometry can be performed on several objects in the sky, not just stars. photometry of resonance space objects helps to characterize the objects and classify them with appropriate plus types and attitude patterns. And with enough stars present in the background image of the resonance space object image, the positions of the stars can additionally be used to determine the orbit. That's kind of all that I have for today. Does anyone have any questions?
Question for you, Michael. Are you able to sort of pick up if a satellite's orbit is degrading through what you're observing, or can you get to that level of detail?
Yes. So eventually, what you can do is either through continuous orbit determination or initial orbit determination, you can figure out if it's degrading and actually where it's going to splash down.
Oh, cool. Okay. Are there any other questions? I don't see any in the Q&A box, but we'd love to follow up with you in a year after you've got some more work under your belt there and see what sort of things you've discovered and how many corrections you've had to give to NASA.
They probably won't. I don't know if they'll accept my my correction proposals. We'll see.
Well, it doesn't hurt to sort of say this doesn't look right, and they may look into it. But yeah, fascinating stuff, and it's all done in Python.
Yeah. So everything's done in a Python notebook. You can use for orbit determination, orbit correction. You can use this ORCID library. I believe it's a Python wrapper for Java. But yeah, everything's done in Python. So everything's open source. Everything's available for everyone to use.
Oh, super. Thank you very much. Okay, so I'll get you to stop slide sharing. I'm going to spotlight Andrea here. Just going to talk to us about clouds on Mars. And good thing we don't have folks trying to observe from Mars these days sometimes. Okay, there we go.
Okay, hi, yeah, so should we go to the first slide, Chris, when you have a moment? This presentation really just arose out of some observations I made over the last couple of months, and then it sort of grew, and so they made it a little presentation. All of the images that I took that you will see were taken with Celestron 11-inch Schmidt-Cassegrain. I use a monochrome camera, the 290 mm, and RGB filters. And usually I use a 1.5 Barlow. But I ended up taking a bunch of images, trying to get a nice picture of Mars. We didn't have many nice nights, but I noticed a few things that got me thinking. Next slide, please. The most obvious feature of this apparition of Mars this time was the North Polar Hood. And it was very, very visible in almost every single kind of image that we saw from our group and in others. And it's not the polar cap, it's actually a cloud layer that hovers over the northern pole, and it forms over winter. Next, please, Chris. I also noticed that I had some other kind of strange looking cloud things. Some clouds along the southern edge, which we're going to talk about, is called the morning mist. And then I was wondering if I actually captured something called orographic clouds, which are clouds that are formed over mountains. So this led me down a bit of an investigation to see if I was actually taking a picture of clouds on another planet. Next, please. The more I looked into this, it turns out that this happened to be a pretty good apparition for clouds, and that had to do with the season on Mars. This opposition, which happened in December, took place at what's called LS 351, and I'll explain what that is. But basically, it's late winter in the north. So this large polar hood, these icy clouds, formed over the long winter. And as we are approaching spring in northern Mars, they were starting to dissipate and increase the humidity on the planet. And so the fact that we were observing Mars at this period in its orbit meant that we were going to be more likely to see clouds than in another kind of opposition. And most people tell you that if you're going to look for clouds on Mars, you need to look at it in the blue light. So taking RGB images with a monochrome camera would help me in that endeavor. Next, please. This is a diagram that sets out the orbit of Mars and helps elaborate on what's going on. As you can see, I don't have a pointer. So where it says perihelion is where Mars is closest to the sun, and it happened to be also closest to Earth. And it appears very large. For example, the apparition in 2020 when Mars was huge was an opposition that occurred when Mars was very close to us. On the opposite end of the orbit is the aphelion oppositions, when Mars is actually really far away and it never gets very big. And hit the next button, because there should be a little star that pops up, Chris. Little animation. Ah, there it is. So that is where Mars was in its orbit in December of 2022. I just want to point out a couple of things. The inner diameter, you'll see degrees, and you'll see there's a 0, and that 0 marks the spring equinox. And the star is LS 351, which is where we were in December. And LS means solar longitude. So that opposition, as you can see, was just before the spring equinox. Next, please. So there are 3 or 4 kinds of clouds that I think I saw, and I'm going to talk about them briefly. I spoke about the polar hood. The polar hood in the north tends to be very bright for some reason, much brighter. The clouds are formed of water and carbon dioxide, and we're not entirely sure how much water, but there definitely are some water in the clouds on Mars. And as we're heading into spring, the north is warming up, then the south cools. So we're also starting to see the development of a southern polar hood, which is a much duller color. There are morning and evening mists, and there are also orographic clouds near the very tall volcanoes of Mars. Next, please. Just so it's clear in this image, all of my images are north up, and P means preceding limb, which is the evening on Mars, and F is the following limb, and Mars will be rotating from left to right as you see it over the course of a night. So some people do Mars, like to image Mars south up, but I'm not doing that. They're all north up. Next, please. All right, so it all began on December 9th, Universal Time. It was actually the evening of the 8th, 1 day past opposition. Can you hit the slide, please? This was an image that I took, and I did a color combination. I wasn't very good at it, so you can see there's a little bit of overexposure happening. Turns out I think it was in the green channel. But you can clearly identify 2 features on Mars, and those are 2 very large mountains, Elysium and Olympus. And next slide, please. Many of you know that Olympus is part of a mountain range on Mars called the Tharsis region. Hit the next slide, please. And I've identified them here, and there are 3 volcanoes in the Tharsis region, and Arsia Mons being one of the very biggest ones, but most of them are in the northern hemisphere. So they tend to be the areas where you will see orographic clouds. Next, please. I don't know if I describe them. Orographic clouds are formed when warm, moist air hits the mountain, it rises up the mountain and cools. And that's a same mechanism as we have on Earth, also happens on Mars, as it turns out. So looking at this picture in more detail, I was able to identify the features. I thought I saw some mist along the southern morning edge, and I also thought I saw orographic clouds. So, are these clouds, or is this something that came from my processing? I went to look deeper into my individual subs. Next, please. So one thing you'll know if you do ever image Mars in red, green, and blue is the blue channel looks totally different. You really can't see any of the features of Mars like you do in the red and the green. That's where you're supposed to see the clouds. Next, please. I'm not entirely sure why, but that is where you look for clouds. So this is a close-up of the blue channel on that day. And when I looked at the blue channel, I was like, I for sure have clouds. It's very easy to see Olympus Mons, and you can identify a big white patch below. And you also see the beginning of a southern polar hood, and there's clearly some mist along the bottom. It's called the sunrise mist. So that was quite interesting. Next, please. Okay. Because I had an overexposed green channel, I wanted to make sure I saw clouds, so I did a synthetic green channel. Next, please. And when I did a synthetic green channel, it was even more clear that I had, in fact, taken a picture of of orographic clouds and a mist. Next, please. To make sure I, sort of consulted with the group. And this image is a composite of several images that were shared in our mail group from various different people. And there's two people actually that also had really nice Mars images, but we didn't fit them into the slide. And I'm going to point to next image, please. Next slide, Chris. There were only two images that were taken at around the same time when Olympus was visible. Starting from the upper left, moving across, Mars is turning over time. And some of you may or may not know, CM is the term for central meridian. So when we look at Mars and we want to identify a feature, we look to the central meridian. So Steve McIntyre took an image of Mars with, I think he did monochrome camera as well, on a, not the same night, but on the same central meridian. And it's pretty clear that he also imaged clouds in about the same area that I did. Next, please. And if you feel really sad that you missed the clouds, the good news is that the next apparition of Mars, Chris, can you hit the button? Yes. This is where Mars will be in its orbit at the next time it comes around in about 2 years. It's going to be at LS 30, which is just after the spring equinox. And as you can see, it's heading into a very long and cool spring and summer in the north. So we expect there to be a lot of cloud next time around. Mars won't be as big, but there should be a lot more clouds. So we have time to get ready for the next time Mars is nicely placed in the sky. Okay, and then next, before we end up, I just wanted to talk about this topic because it's actually a real life astronomical drama that's happening right now amongst Mars observers. The blue clearing was something I heard about when I went to look at a Mars certificate with the Astronomical League. The ALPO is the Association of Lunar and Planetary Observers, and they have a wonderful guide for Mars observing and actually all the planets as well. They describe the blue clearing as a phenomena when the surface features of Mars can be seen and photographed in the blue light, in the blue and the violet light. So in other words, what I showed you before, where you just see a blue image and it looks totally featureless, every once in a while the blue clears and you can see features. This can be done with imaging, or it can be done with a violet filter, the Raton 47, or a deep blue filter. And according to the Astronomical League, to get their certificate, you have to make 4 blue clearing observations. So this sounded pretty complicated. So I asked some people about this. Next, please. On cloudy nights. And I came across a thread, which I thought was super interesting. It was commenced on cloudy nights by Christophe Pellier, who's the person in charge, I think it's of the French Planetary Observing Group. And his view that there was no such thing as a blue clearing, it was an opposition surge effect. In other words, when a planet is in opposition, which is opposite from us, Earth is in the middle and the sun and the planet are opposing each other, it's very bright, it's very well lit. And that's why we can see through features through the blue light. He doesn't believe in the blue clearing. And this is also supported by ISMO, which is the International Society of Martian Observers. So he doesn't like it when you call it the blue clearing. He doesn't believe in it. The Astronomical League people, they still believe in it. So regardless, I went to see if I could have any blue clearing. Next, please. So these were some images that I took in this is December. This is very close to opposition. And if you see in the green and the red and the RGB, there's a bit of a snake-like feature that's visible. In my view, it's very visible in the blue as well. So that would count as a blue clearing, but it's also at opposition. Next image, please. on this day, December 15th, a day of totally horrible seeing, I can also see a little bit of the features as well. Next, Chris. And so I wasn't sure, was I really seeing the blue clearing, or sometimes, how do I say this, inexpensive red, green, and blue filters have a leak. They have a leak in the infrared, and I'm really just seeing infrared. So I got a new set of filters, and don't ask me how many filters I have at home now, but this is a different set of filters, and in the blue, I think you can still see the features of Mars visible in the blue light. Next one, Chris. And by January 10, I could see a little bit of the blue clearing, but it was definitely starting to fade. So I don't know if this is a real thing. I don't know if it's an opposition thing, but if you are interested in learning more about the blue clearing and Mars and clouds, next slide, please. These are two places that I found had a lot of really good information. One was the Alpo website. And this is also a book, and this book happened to be written by Christophe Pellier. And as you can see, this is a photocopy of my book. It's well worn, it's falling apart now, but it's a really great book for both observing and imaging planets. And it covers all of the planets, and it's a really, really well-written book. It's recently been translated to English, so you can get it now in English. That's my presentation on Mars. Thank you.
Okay, are there any questions?
That went very fast, but I was told I had to be fast. So if anybody has any questions afterwards, you can also please know where to find me.
Yeah. Okay, I don't see any questions right now. I also have the planetary astronomy book. It's excellent. So I highly recommend that publication. Okay, so where are we at here? Richard, let me spotlight you. There we go. Sorry about that.
Thank you. Now, I'm going to be trying some risky things here, trying to actually run some programs in real time and show how they work. So let me start sharing my screen. So a few months ago, when I was doing some of my observation presentations, I mentioned plate solving as a method that I've been using to help me find my way around the sky. And Mick turned around and said, well, you've mentioned something new and you're the expert now, so tell us all about it. Plate solving, what is it? And why do you do it? Well, actually, plate solving, it has a very long history, and the word itself refers back to the old glass plates. So if you want to do plate solving the traditional way, you have to be taking photographs on glass plates through a large telescope. And then you hire a computer like Annie Jump Cannon to actually look very closely at the developed plates, usually in a negative form, and try to identify where it is in the sky, what objects you've found, what stars are there, and catalog these photographic plates. So that's the traditional way, but now, of course, our computers are all electronic, and we do it using software. So why would you want to do this as an amateur? Well, my first application was to try and help me with star hopping. I didn't have a go-to mount, so I couldn't just type in the coordinates of something and have it automatically go there. I had to find out where I was pointing and shift the telescope manually to find where I wanted to go. And from my Ottawa sky, that was pretty hard. And then eventually I did get a new mount that does have the go-to capability, but I still had to do polar alignment. And I found out that plate solving is also useful for polar alignment. And my field of view in my camera that I'm using most of the time these days is very small. Some objects are just too big to fit in the field of view. So I need to produce a mosaic of multiple frames stitched together to try and cover a large nebula or something like that. And plate solving is useful for that too. And very recently, in the last few months, the tool that I normally use now for my image processing, PixInsight, has come up with yet another application, the precise color balancing of the stars in your images using plate solving. And finally, you may have seen in many of people's observations identification of the objects they've found. Well, plate solving can help with that too. And there's probably many other reasons that I haven't discovered yet. So let's go into some more detail on a couple of these applications. I'm going to try and keep this brief, so I won't go into the details on all of them. But to show you how straightforward and easy it can be, I'd like to do a live demonstration of something that you could actually do. If you have an astrophoto of any kind, go and start up a particular website. Now, astrometry.net. The address is actually nova.astrometry.net. And if you go here, you can upload your own photograph. Choose a file that you've got on your computer. I'm going to take a picture I took of some galaxies. And this one I haven't tried out before, so we'll see how it works. I haven't even signed in. I'm just doing this as anonymous. They say we'll have the results within 10 minutes. So there's my picture. They've loaded it. We'll come back to that at the end of my presentation and see what happens, okay? Meanwhile, let's look at the application that I first started with, star hopping. So there I was with my Ottawa night skies. You can barely see very many of even the brightest stars. I wanted to try and find my way to Uranus, a 6th magnitude planet. No way was I going to see it visually. And it was in a pretty empty region of the sky too, so there wasn't anything really nearby. So roughly aim it based on Jupiter and some other things that I could see. Nothing. What have I got? I had this picture. Let me show you what I was seeing on my screen. That. Some stars, all of them pretty faint, but that's what my camera was seeing in the live view. Now, normally before plate solving, I would then open up the Stellarium program, the sky map. It can find Uranus quite easily, but where am I? And I would have to look all around at the nearby stars. Is there any pattern in this area that matches my picture? Well, I see a triangle here. And I see a similar looking triangle right here. Yes, it's a different orientation, but that's quite typical. The camera can be oriented quite differently from what the sky map shows.
I think you need to scroll down a little bit, Richard. Are you trying to show us the Stellarium image?
This should be showing Stellarium right now.
No, you're just part way up the screen. So just scroll down a little bit.
I'm seeing it full screen on mine.
Okay, yeah. What we're seeing is you're showing us your desktop.
Okay, I need to minimize this one then. And I have to do a new share.
Yeah, we're just seeing off your webpage only
Gotcha.
right now.
Okay.
You may want to stop the share and then, okay,
Yes.
that's good. Yeah.
Now you're seeing stellarium.
Yeah.
And what I was trying to point out was in my picture here. That's what my camera was seeing. There's a triangle of 3 stars here that looks similar to this triangle here. So maybe my camera is down here. But it turns out that I was wrong. And when I tried plate solving, I found my mistake. So let me try and show you the plate solving. Nope. Nope. It's not showing up. Oh dear.
Maybe use stop sharing and
Yeah,
find the plate solving and then share and point to that. Yeah.
It's showing new share.
Okay.
Stop share. Just a moment. Put that on the screen and share again.
It's a stacking program.
Okay. So you can now see a step. Okay, so this is a free program that's available on the web. You do have to download both the software and a database of stars, and then it can find your pictures within that database. So in order to use it, there's a couple of steps that you have to be very careful about. If you load a FITS file, which is a common one for astrophotographs, it will have some data about the camera that you are using. If you don't, if you use a JPEG or some other format that does not include camera information, then you're going to have to enter information about your camera and telescope. So it's a bit hidden. You have to click on the stack button here, go to Pixel Math, and actually set up the telescope focal length. Mine happens to be 430 millimeters. And the sensor pixel size. It got that from the FITS size. I found out just yesterday as I was rehearsing for this talk that you also need to pay attention to the size of your image dimensions. It should be able to calculate this automatically. Sometimes it didn't do it. So check that this field of view in the alignment tab does match the height of your image here. So once you've got all that done, you can then solve the image. And literally within 0.2 of a second, it can find where that image is. And it will recalculate your, oh, sorry, that was something I forgot to say. You do have to estimate where it is in the sky, right ascension and declination. Very roughly, it can be within 20 degrees, so it's not a big deal on that. But you do have to have those, and then when it does the plate solving, it will tell you exactly where you are. Now, going back to stellarium, I'm at 249, 1528. Are you seeing stellarium?
Yes.
Okay. So looking at my RA and deck of my field of view here, 249, 1528 is actually 249 there. So that was my little mistake I made. I thought I was seeing this triangle. I'm actually seeing this triangle. And you can tell there's also another isosceles triangle here in my image. Let's see if I can go back to that. Yes, there is that triangle there. So now I have found exactly where I am in the sky and also relative to Uranus. And I need to move my telescope to push those triangles out of the frame down this way, and then Uranus will be in the field of view. And that's how I actually used it. By doing the plate solving, I could find out where exactly my telescope and camera were pointing, and then I could move it appropriately. And even when it was quite a distance away from my target, I could usually find it within 2 or 3 steps. So it's quite a good tool for automated star hopping. Now, as I say, I did buy myself a go-to mount, and then I found a second application of plate solving, which is polar alignment. So the new telescope doesn't have a little telescope along the polar axis. Instead, it has a camera, and it takes pictures of the region around the North Pole and tries to help you find where your polar axis is relative to the true north. Now, I can't do this one in real time because I'm not going out in -27 temperatures to set up my telescope, but I do have some screenshots of how it looked. So let's see if I can switch over to a bigger view of this. There we go. So with the telescope roughly pointed towards north, turn on the camera, set it up, it starts taking pictures of the stars around the North Pole. And it can start plate solving to identify where I am. In order to find the actual place where the axis is pointing, it needs to know the effects of rotation. So I have to rotate the telescope around the right ascension direction and take another picture. Then it will then be able to find out where the axis of rotation is. So it marks that with a red dot on the screen, and it can also mark the true north position with a little cross on the screen. So now I know that my polar axis of the telescope is not polar aligned. It needs to be shifted a little bit over, a little bit up in order to get it pointing true north. And you can actually do that while the camera continues to take pictures. It's taking a picture every 250 milliseconds. And you can then adjust the azimuth, the sideways motion, and the altitude, the up-down motion of the polar axis, until you get that little circle and the cross lined up. When you do, when you get it close, in fact, it will start zooming in and showing you this kind of version. the cross is not quite on top of the circle. And then when you get it perfectly, it will turn green and show you, yes, you're perfectly polar aligned. So generally in practice, this takes 5 minutes or so. It makes it quick and easy to polarize and quite accurately too. So that's the second use that I found for the plate solving techniques. I'm not going to go into too much detail on the other ones, but the third application I found quite useful is taking mosaics. Generally, if I'm trying to piece together my photographs into a mosaic, there's a real problem at the edges. They don't line up quite properly because generally astrophotos have a slight distortion, especially around the edges. To get rid of the distortion, you can actually run a plate solving routine and align your stars in your picture with a map of the stars. And that can be done quite automatically in PixInsight. It works beautifully. And that was the result, a 2-panel mosaic of the Orion Nebula. And then there's another application which I'm only just starting out with, but it turns out that it's very similar to Michael Stewart's application from earlier this evening. And that is getting the right colors for your stars. If you plate solve your images, find out exactly where you are and what stars you're seeing, you can actually go into a database, the Gaia database of spectral information about the stars, and find out what color they should be. And then calibrate the white balance of your image to match the best possible known values of the colors of the stars. And that's again what PixInsight can do using the spectrophotometric color calibration process. And you can see on the side screen here, some of the graphs very similar to what Michael Stewart was showing earlier. And there's probably a whole bunch of other applications that I haven't even discovered yet. But let's go back to astrometry.net and see if it's managed to find my galaxy picture yet. Oh yes, success. It has actually found where this is. So let's go to the results page and look at it full size. I hope. Yes. And I had M100 right in the middle. But not only that, I had found several other galaxies, as you can see them marked here, with their NGC numbers and IC numbers. So actually, I've got quite a number of different galaxies there. So that is something that I think you can get started with right away. If you're interested in this kind of thing, if you've taken any pictures of the night sky, run them through astrometry.net and identify objects. On a wide field view, it will actually identify constellation boundaries, constellation lines and stars. On a more zoomed in view like this, you'll be finding all kinds of galaxies and nebulas and such like. For a little bit more advanced work, I do recommend the ASTAP program. This is where you can download it. It's from hnsky.org. And as I say, you do have to download both the program and at least one of the databases of stars in order to make it work. And then, of course, if you're into more advanced image processing, PixInsight is definitely the tool to go. It is pricey, but it's certainly worth every penny I paid for it. Okay, that's all for me. Any questions?
Any questions, folks, for Richard? Don't see any here. Let me just check the chat. No, I think we're good to go. So thank you very much, Richard. And again, if you have any questions over the break, just feel free to post them. And Richard will be staying on the call till the end of the evening.
Okay, this should also be, there should be something like this in Astronotes this month, and I hope on the website too. So if you need the addresses and so on, that's where to find them.
Okay, thank you very much. And it is time for a break, and let me just replace the spotlight. There we go. Okay, so while we have a 5-minute break, the planets make up what percentage of the mass of our solar system? So you've got 4 options there. Take a wild guess. If you want, you can post them to the chat window to everyone, and we'll see who gets the prize. Okay, we'll see you in 5. So, folks, we got about a minute left, and then we will resume. I will see we've got some guesses in there already in the chat, and let me see.
Coming to 2 of the 4 possibilities.
Yeah, I can tell you that in the chat, 2 people, 3 people have it right. Okay, let's resume. Let's see how we do in terms of the trivia for tonight. Yeah, a bunch of you did get it right. It's 0.135. Of course, the sun's the largest, 99.86. And the satellites and comets are a very, very small percentage of the overall mass of our solar system. So next we have Rick Wagner, who's going to be talking about astronomy with the RASC remote telescope. So take it away, Rick.
All right. Thank you very much, Dave. It's great to be back talking about the remote telescope. Last month, I talked about the telescope itself, what it is, where it is, and how we run it. Tonight, I'll talk about its prospects for scientific observing, some of the things we're thinking about doing, and some of the things that we've done. Next slide, please. So here's a picture of the instrument and its building in the Sierra Remote Observatories in the Sierra Nevada Mountains in California. Next, please. So just to cover quickly what I did last time, it's a 16-inch Cassegrainian, Ritchie-Chrétien Cassegrainian f8.9, 3.5 meter focal length on a Paramount ME, and piggyback on it is a Canon 6D Astro modified with a 200 millimeter f2.8 lens. Next. The camera is an SBIG STX 16803. So that's a 4K by 4K chip, 36 by 36 arc minutes field of view at a half an arc second per pixel. It has an off-axis guiding chip, and there's the gain and read noise if you're really into the numbers. Next, please. Accessories, an AOX adaptive optics unit, a 7-position filter wheel, fully populated with all the pretty picture filters, and an image rotator. Next, please. Software, we control it all using VNC over the internet. The SkyX is our planetarium mount and camera control software. Focusing is with FocusMax. Backyard EOS runs the Canon camera, And then we do generally scripted observations using either CCD Commander for most of the science work and CCD Autopilot for most of the pretty picture work. Next, please. The site, Sierra Remote Observatories, at an altitude of 1,400 meters. The SQM readings are generally around 21 magnitude, a little bit lower. And they have fiber internet for fast upload and download. All right, next, into the new material. So the first thing we care about when we're taking scientific images is we don't want to saturate any of our stars. Once a star begins to saturate, it effectively stops responding to any light. Dimmer stars in the image will continue to get brighter, but our brightest stars will pretty much stay at their same brightness. So we want to avoid doing that. So I took a whole bunch of pictures of M67 actually, which has very carefully calibrated magnitudes, and then measured the brightest star that was unsaturated at each exposure and made a table. You do that again for each filter. So now, for instance, if you know you're shooting a 12th magnitude star, you can read off of this table what kind of exposures you should limit yourself to. Next, please. So the next thing you're interested in is what kind of a signal to noise ratio are you going to get on your stars? If you're doing photometry of a star, say with a large amplitude, you can get by with quite poor signal to noise ratios. So what I did in this case was, again, took a whole bunch of pictures of M67 and then measured the signal to noise ratio of about 500 stars on each image and did that in each different filter, created this table. And so you can see down the left-hand side are star magnitudes and across the top are exposures. And then inside the table, the number is the signal to noise ratio. Now you'll notice down in the left corner, it's all blank. That's because those are signal to noise ratios below about 10. And in the upper right-hand corner, they're highlighted because when you get into that area, you're very likely to be running into saturation on some of your brighter stars. So you need to adjust your technique somehow to avoid that saturation or just change your exposure. Now, the interest in the signal to noise ratio is that, for instance, for photometry, the accuracy of your photometry is very roughly equal to the inverse of the signal to noise ratio. So a signal to noise ratio of 100 will give you approximately 1/100th of a magnitude accuracy on your photometry. Now, for most stars, 1/100th of a magnitude is quite adequate. But for instance, if you're shooting exoplanets or very small amplitude variables like delta Scutis, some of them don't even have 1/100th of a magnitude amplitude. And so shooting at a signal to noise ratio of 100 would be wasting your time. Next, please. So this is a little detail into what Michael was talking about earlier. The filters that are in the camera are the pretty picture filters. They're not the Johnson-Cousins photometric filters that we would like to use. So why do we care? Surely a blue filter is a blue filter is a blue filter. Well, it isn't. So next, please. So you can see we have here two blue filters, supposedly both Johnson-Cousins filters. And I've plotted, these are their band passes as a function of wavelength. And you can see one is a little bit offset from the other. So then I've also plotted the spectral energy distribution, basically the brightness as a function of wavelength for two stars. The yellow line is for a star that has a surface temperature of 5,500 Kelvin, And the green line is one that has a bright temperature of 7,500. Next, please. So you can see in the highlighted filter here, the two lines of the stars cross approximately in the middle of the filter. So at the longer wavelengths, the 5500K star is slightly brighter, and at the bluer wavelengths, the hotter star is somewhat brighter. And those two average out so that they come out with roughly the same magnitude if we measured these two stars with this filter. Next, please. With the other filter, you can see that the 7500 star is brighter almost across the entire bandwidth of the filter than the 5500K star. So in this case, the 7500K star would be significantly brighter in our measurements. And obviously we don't want the magnitudes of the stars depending on what brand of filter we're using. Next, please. So we do what's called the transform that Michael talked about. Essentially, you measure images of standard fields with very well-known magnitudes and colors, and you work through the equations and you come up with these equations. The first one you can see relates our TB, which is the tricolor B magnitude, and our tricolor green magnitude to give us a Johnson B minus V color, and then we can use that with the transform coefficients to determine a V magnitude. So this involved, again, a couple of dozen pictures of M67, plotting all the data and coming up with the transform coefficients as Michael showed. And what I determined is that the conversion from the green filter to a V filter and the red filter to the Johnson R filter are both pretty good, probably within 1/100th of a magnitude or so, but the B filter is quite a bit worse, maybe as much as 0.05 magnitudes. So I tend not to use it. In fact, most of the photometry I do is actually with a clear filter, and I use V magnitudes as the standards. It's what's known as a CV magnitude in the AVSO. So next, please. So the last thing, major project I undertook was some minor planet astrometry. I took pictures on several different nights, spaced a week or so apart, of 3 different asteroids, did the astrometry rather on them, and submitted all the observations to the Minor Planet Center in the United States. And once they had verified the accuracy of the results, they assigned us an observatory code. So now in the future, anybody who's interested in doing astrometry, we can immediately submit observations to them for orbit improvement, etc. Next, please. So the scope has some limitations. The first one is 3 to 4 days between sessions. The science team gets Monday and Friday nights. The pretty picture people get 3 nights, and Samantha takes Wednesdays for outreach, primarily doing exoplanet transits with high school students. So there was a lot of interesting events or periods of variation and stuff that with a 3 to 4 day interval between sessions, you can't really manage to detect certain types of variation and so forth. So that's a limit. I mentioned the non-photometric filters. We're hoping at some point we may be able to upgrade to a larger filter wheel, and then we may be able to get some photometric filters in there as well. This is a big 16-inch telescope, so anything brighter than about 6 magnitude, you're going to have a very hard time dealing with it. On the other hand, it's only a 16-inch aperture telescope, which means anything fainter than about 20th magnitude is also going to be very tough. I shoot 2x2 binned images, and these take 16.6 seconds to download. So if you're shooting 10-second images, you're actually spending more than half your time downloading and less than half your time observing. So that starts to get rather impractical. And finally, the mount itself has very good but not perfect tracking. So most of the time we limit ourselves to 2-minute exposures. I am just starting to get into using the CCD autopilot, which does have auto guiding, and I'll use it for some of the very dimmest targets. Next, please. So I wanted to come up with a list of interesting projects that might get people excited about the idea of getting into the science team. So first idea is astrometry. Seems to be a topic of the evening, measuring the position of objects in the sky. Trans-Neptunian objects, they're very faint, but doable with this scope. Unfortunately, those and minor planets as well, there's hundreds of thousands of minor planets, but they're generally pretty well observed. Minor planets particularly. For instance, if you just take 2 randomly picked minor planets, say 10486 Terran or 10059 McCullough, when you ask for the ephemeris from the Minor Planet Center, it tells you right up front, we don't need any more observations of those. We know what their orbits are doing. Everything's fine. And that's the way it is for almost every object that's brighter than about 20th magnitude. However, there are always new comets appearing, which may not have good orbits, and cometary orbits do change as well. And of course, there are always new near-Earth objects, which may not be well measured. So those are 2 things that, that we could do astrometry on. Next, please. Searching for objects, that was always a big thing for amateurs. Searching for minor planets, when I first started imaging, it was not all that difficult to take, a few hundred images of the sky and discover some new minor planets down around 16th, 17th magnitude, maybe 18th magnitude. Now, if it's brighter than about 22nd magnitude, there's probably lots of people already know about it. Supernovae, very similar. That used to be a thing for the really advanced amateur. Unfortunately, now with the very big all-sky, deep sky surveys, they're discovering like a dozen supernovae every night, which is more than anybody needs to deal with. So. Supernova light echoes is something that Doug Welch originally talked to me about. These are basically reflections of the flash of a supernova. If you can think on the cosmic scale of a supernova as being like a flash bulb going off, there's a shell of light that flashes out from the supernova, and years later, even centuries later, it can reflect off clouds of dust and gas, and the light makes its way to the Earth. And so you can actually detect these supernova light echoes and actually get a light curve of the supernova from centuries ago.
We have a question, Rick.
Okay.
What qualifications are necessary for joining the science team?
I'll get to that later.
Okay. Thank you.
Coming. And the other thing I thought would be interesting is looking for ultra-faint dwarf galaxies or star streams around some of the large nearby galaxies. Not necessarily very practical or very scientific, but if you can use it as an excuse to do ultra-deep imaging of nearby galaxies, that's always a good thing. Next, please. So getting into photometry. Well, of course, photometry is my obsession, so I may be biased, but I think this is the best place for the amateur to contribute to science. minor planets and trans-Neptunian objects. Most of them rotate, most of them are oddly shaped or have patterning on their surfaces that cause them to vary in brightness. So you can do photometry of them and measure their rotation periods. If you get into it in real detail, they can actually use computer programs to actually calculate the shape of a minor planet. Variable stars, of course, there are dozens of different types of variable stars and literally hundreds of thousands of known individual variable stars. So there's lots of work that could be done there. Imaging clusters, either globular or open clusters. One little project that I've been trying to do at home is doing HR diagrams, color magnitude diagrams. They have various names, basically to measure the age and the distance of clusters. And also you can do variable star searches. There are a lot of variable stars with periods which are not easily captured by some of the sky surveys. Extragalactic variables, I've at home have been imaging M31, Hubble's first variable there. And I think we're going to get into a project with the remote telescope of trying to do some variables in M33. Exoplanet transits, of course, are a big fad right now. And doing very careful work on exoplanet transit timing variations you can possibly find evidence for orbital changes, rotation of the orbits, possibility of moons around some of the exoplanets. And another interesting place to work is the TESS satellite. Has very large pixels. So when it finds a candidate, they don't necessarily know if it's actually an exoplanet transit, or maybe it's an eclipsing binary that just happens to be in the same pixel. And so they need amateur astronomers to image a lot of these things, do photometry on them, and confirm whether these are actual exoplanets or not. Next, please. So some of the work we've done so far, the team has been working for about 3 years now, developed fairly slowly over the first year as we figured out what was going on and all the measurements that we had to take to make the scope usable in science. But we're doing well now. We've taken a total of almost 40,000 pictures. On about 220 nights, I think, so far. So next, please. So here's a picture of M61 with the supernova from 2021. We did a bunch of measurements of that and submitted them to the AAVSO. Also did some of a supernova in NGC 3463. Next, please. So here's a stack of 10 400-second exposures of part of M31. This is the full frame of the camera. The limiting magnitude here is about 21st with a signal to noise ratio of about 3 at that magnitude. Next, please. So if we crop it and zoom in, you can see the little black tick marks. That's Hubble's variable number 1 where they intersect. So that was the very first extragalactic variable star ever detected. And that's the one that caused Hubble to realize that these spiral nebulae were in fact isolated galaxies separate from our own. The universe got enormously larger at that time. This one runs from about 19th to 20th magnitude, and that's about the limit of the photometry we can do. Next, please. So here you can see I did 6 measurements with the 16-inch telescope, the little green squares. The red plot is a rough light curve for this variable. So you can see the measurements are within 1/10 of a magnitude or so, which is what we expect from the signal to noise ratio we're getting. The little dots across the top are the check star, which we use to make sure that the photometry is going well. Next, please. Also in that image of M31, we happened to catch a NOVA AT2020 YPU that just happened to go off some days in advance of when I was doing those images. You can see it's barely detectable, and I don't think photometry of this thing would be of any use at all. And I don't think it's bright enough that I would want to be hunting for things like that. Next, please. So we've done several thousand measurements of several cataclysmic variable stars. These are stars that basically a white dwarf or a neutron star orbiting a normal star, and it's sucking matter off the normal star into an accretion disk. These things are very complicated because of the different star sizes, the different compact object, the magnetic fields, the rate of flow from one object to the other, and so forth. But here's one evening, several hours of observations of HP Libre. And quite frankly, I was mortified when I looked at this massive scatter and thought, well, something's wrong. Next, please. However, if you connect the dots, you discover that we've got this fabulous light curve, beautifully showing 16 cycles of its 18.9 minute period. So this is the, I think, the orbital period of the binary system. Next, please. So another project we've been working on is high amplitude delta Scuti variables. These are stars that are maybe twice the mass of the sun. They're still on the main sequence, and they pulsate by the same mechanism that causes Cepheids and RR Lyrae stars to pulsate. Now this one, you can see this is 3 nights of data plotted in different colors, and they all overlie each other beautifully. So this is what's called a monoperiodic star. It's basically just pulsating inwards and outwards, nice and simple. It's a 1.9 hour period. This is why I like delta Scutis. They do a lot in one evening. Next, please. Here's another one. I'm not even going to read off its name. It's an ASAS object, so it's basically just its RA and DEC. This is a string of, I think, 8 hours observations. We've done this one 14 nights, about 500 images. You can see that the peaks are not all the same. And this is a result of it having actually 2 periods that are interfering with each other. So it's got an 81-minute period and a 63-minute period. Next, please. So this is a star that we've been observing for a long time, and V3124 Cygni. It's the sort of fairly brightish star right in the center of the field. It's got a reported period of 2.1 hours, and we've taken, yeah, that's the one. And we've taken 3,840 pictures of it. So next, please. I'm going to show you all the, no, I'm not going to show you all the pictures. Here's a graph of, let's see, what was this? This was 3.6 hours of data taken one night. Lovely light curve. You can see the nice characteristic shape of the rapid rise to maximum and then the slower decline to minimum. It's a little odd that the 2 minima are not the same depth, but maybe that's not a problem. Next, please. Same star a few nights later, and the light curve looks completely different. Next, please. Well, now this is getting silly. This is another night, and it looks completely different. This is odd. So next slide. We plot all the data, we phase it all by the 2.1 hour period. And in theory, this should all end up as a nice uniform line of all our observations from each night overlapping. And what you can see is we've clearly got some sort of a signal at 2.1 hours. But on the other hand, it's a mess. There's, you can see individual nights of data wandering through this band. So what we do next, please, is we take all our data and we hand it off to a program like Period 04, or there's a new Python version called Pyriad. And basically what it does is a Fourier analysis of the light of the data. It fits sine waves to the light curve. And what we find is it's got two frequencies at 9.5 cycles per day and 11.4 cycles per day. But then there's also all kinds of combination frequencies, frequency 1 plus frequency 2, 2 times frequency 1, or frequency 2 minus frequency 1, additions and multiples and so forth, going right down to about 2 millimagnitudes variation. So what we do is we take all this data from the model and we can plot that along with our data. Next, please. And here you can see the red dots are the observations and the black line is the fit from the model. Next slide. Again, very good fit. Next, please. It's even caught that weird night. Next, please. So if we plot just the model itself, here is what the light curve of that star would look like over, I think, about 2 days. So it's definitely, this is a very unusual star. These stars normally have a period of about 0.78, or a ratio of 0.78 between their periods. And this one is more like 0.85 or something, 83, which is very unusual. So there's definitely something odd with this star, and it's definitely going to be worth keeping an eye on. Next, please. So the goals of the telescope, we're going to get into some of the administration and so forth. I think the most important thing for me is InReach. This is a facility that the members can use either for the pretty picture side or the science team. Probably also use it for outreach if you were willing to get into that side of things. We intend that this should be a learning experience. Members of the science team and the photography teams should be learning how to plan observing projects, figuring out what data they need, analysis of the data, publication, and so forth. So both the people doing the projects will learn, I hope, a great deal, and will also publish the data to the membership in general, so they learn as well. And finally, of course, we want to advance the science of astronomy. So actually publishing results in peer-reviewed journals is one of our goals. And as well in Sky News, Sky and Telescope, et cetera, the bulletin of the RASC. Next, please. So administration, this is somewhat to be determined yet. We're discussing it and advancing. We anticipate that the science team will consist of project leads. So this would be sort of your principal investigator on a science project. And then there would be team members. So members could come into the science team with a project lead and work on that specific project, or perhaps join the science team in general and then be there as a resource for a project lead. When he comes in, he would have people who could help him with or her with data analysis, writing papers, and so forth. How to join the science team? Essentially, right now, I think the plan is that you ask, can I be on the science team? And as long as the size of the team doesn't get out of hand, we'll probably let you join. We're working on how to assess proposals. We're anticipating that project leads will submit a proposal for observations. And right now we have an assessment procedure, which is hugely complicated, but we aren't locked into that. And we anticipate that both we and people submitting proposals, this will be a learning experience where we can all get together and figure out what needs to be done, how it needs to be done, what limitations there are, is moonlight going to be a problem, and so forth and so on. And finally, and unfortunately, fees. We have to, there is a drive to make this telescope at least somewhat financially viable. And so we are anticipating there being fees charged. We're not sure what the fees will be. There's been some discussion that perhaps a project lead would be charged a small fee per month, for instance, while they're collecting data and so forth. I can't think of anything else that's important. So I guess next I can take any questions if people have them.
Okay, there was just that one question I called out in the middle there, Rick. Sorry, I should look forward in your slides. Anyways, you did. You answered that question.
Okay.
And are there any other questions for him?
Well, David's Chris, maybe I'll just expand on that question that was asked. And the question was much more so, what qualifications are you looking for of someone wanting to join the team, as opposed to how do you ask to join?
Yeah, that's a good point, Chris. Basically, I think the main qualification would be an interest in learning to do science with the remote telescope, and not even necessarily doing it with the remote telescope, but for instance, to be a member of the team, get mentored on how to do photometry on images or analysis of data, learn some of the software, that kind of thing. So yeah, a desire to learn and an interest in the science.
So Rick, are you the primary contact then?
Well, I wouldn't put myself out as a contact yet. It's probably going to be another couple of months yet before we formally open the team for subscriptions, if you will. So we're working away at it. And another thing that I'm doing right now is I'm writing a variable stars course that we're planning to give hopefully in April. So that'll be sort of a, once a week for 8 weeks or 10 weeks or something, course on all about variable stars. So as we get into April, I hope we'll be making it known throughout the RASC that the team is open for business.
Okay, super. That was one of the questions we had as well. Who to contact? So basically, wait until things are a little more fully developed, and then we'll.
Yeah, and of course, once things are in place, you can always call me and ask me questions or whatever. Yeah.
Okay, sounds good. Okay, well, thank you very much. So we're going to move into our observation reports, and I see Jim Thompson is up. Let me just replace the spotlight. There we go.
All right. Good evening, everyone. My observing report this month begins with the lunar challenges for December and January. Crater Vendelinus, which is marked there in the image, as well as crater Langrenus, which is the large crater immediately above it. This particular image of the waxing crescent moon was captured almost exactly a year ago on February 5th, 2022. Because this lunar phase follows the sun so closely, I had to capture it from my backyard while it was still daylight, around 5 p.m. in the afternoon. This image is in fact a mosaic of 8 separate frames, each of which is a stack of the best 10% out of 3,000 frames. I used a 10-inch Ritchie-Chrétien scope at its native f8 with an ASI 183 monochrome camera and an Astronomic ProPlanet 642 IR filter. Next image, please. In this view, we see a crop taken from the previous image, now displayed at the full resolution. The 147-kilometer diameter crater Vendelinus sits below the much more prominent crater Langrenus. Vendelinus is less prominent simply because it is much older than Langrenus. Vendelinus's rim is beaten down by numerous younger impacts and its floor is flooded with dark basalt lava. Langrenus has a much better defined rim with terracing visible. It also has a well-defined central peak and lots of secondary impact features around the crater's perimeter. In fact, if you look closely, you can see some of the secondary impacts from Langrenus superimposed on top of the smooth features of Vendelinus, confirming that Langrenus is a much younger crater than Vendelinus. I find it challenging to observe the moon at phases that highlight the eastern limb, as their timing is less than ideal. Waxing phases, like my image here, place the moon close to the sun, and so are best observed looking west at sunset, assuming you have a clear view to the west, which I don't. Waning phases are best viewed after midnight, which on a weeknight is not the most convenient time. Next image, please. My next observation is the only observing that I managed to accomplish in the month of December. It is of the sun around midday on December 10th. These two images are captured using a 98mm refractor and the new camera I told you about during the December meeting, the imaging source DMK33UX226. Both of these images are stacks of the best 200 frames out of 5,000, stacked in AutoStacker 3 and sharpened in IM-PPG. Seeing and transparency were both poor that day, what with the sun being so low in the sky, which is why I had to capture so many frames. Note that the images are actually captured in monochrome. I've added color during post-processing. The image on the left is captured using calcium 2K down at 393 nanometers wavelength, so in the near UV part of the spectrum. Using this wavelength of light, sunspots are quite prominent, as well as the magnetically active regions around them called plages. Granules, the fine texture that you see in the darker purple areas, are also visible. The image on the right was captured using a hydrogen alpha tunable etalon, which only lets light in at 656 nanometers. The image is in fact a composite, with a surface detail captured at a shorter exposure than the prominences around the perimeter. Note also that I have inverted the surface detail, so areas that are hotter, such as the solar flares, are dark, and areas that are cooler, such as the sunspots and filaments, are light. Next image, please. This image is a crop of the previous one, showing the more active regions in full resolution. In this case, active region 3157. I've also added a corresponding image using a Bader solar continuum filter, a filter that passes light in a 10 nanometer wide band at 540 nanometers, so right in the green part of the spectrum. I find it interesting to compare different wavelengths as it helps to better understand what's happening. Physically, the solar continuum view is at the bottom of a 3-layer cake, providing us a view of material at the top of the photosphere. The calcium 2K image is of material immediately above the photosphere in the lower chromosphere, and the hydrogen alpha image is of material above that in the middle to upper chromosphere. Another interesting observation is that the areas of the most intense magnetic activity, marked by the bright flares in the hydrogen alpha image do not seem to be associated with large sunspots, but are instead associated with very small sunspots. Next image, please. This image is of the Intermediate Deep Sky Observing Challenge for January, NGC 2174, the Monkey Head Nebula. This nebula is a star-forming region located about 6,400 light-years away in the constellation Orion. The young open cluster of stars being formed by this nebula has its own designation, NGC 2175. This image is a stack of 24 40-second frames captured using a ZWO ASI 533 MC Pro camera and a 10-inch Ritchie-Chrétien scope reduced to f6. I was able to pull out a reasonable amount of detail from my Bortle 9 Plus backyard in only 10 to 15 minutes through the use of a 3 nanometer dual band filter from Optolong called the L Ultimate. The image was captured on the evening of January 15th. Next image, please. And this is my final image tonight. It is of NGC 2359, the Thor's Helmet Nebula in Canis Major. The nebula is about 12,000 light-years away and is formed by the interaction of Wolf-Rayet star WR7's vigorous solar wind with the surrounding molecular cloud. This massive star is in the final stages of its life and is expected to go supernova in the near future, cosmically speaking. The image was captured using the same method and equipment as the previous image. The only processing applied was some tweaks to the black point and white point after the fact, and the application of some denoising in Topaz Denoise AI. That's it for me. Clear skies, everyone.
Thank you, Jim. So we're going to turn it over to Richard Taylor.
Okay, this is the beginner challenge for the month, Messier 35. Messier 35 is the bigger, brighter cluster in the top left, but I found it interesting that it shares a field with another cluster, NGC 2158 in the lower right. And the two clusters are quite different in appearance. I just wanted to note here that this is one that I did the plate solving and spectrophotographic color calibration on. So the colors are somewhat real. I did boost the saturation a little bit to bring out the color a little bit more, but definitely M35 is a fairly young cluster and it has a lot of very bright blue stars, as you can see. And NGC 2158 is made of quite a lot redder stars and is expected to be quite a lot older. They're also at different distances. M35 is about 3,000 light years away, whereas NGC 2158 is about 15,000 light years away. So quite an interesting contrast there. Next one, please. Here's another clear night in Ottawa. I don't have any special filters on my cameras, so it's kind of hard to pull out nebulas against the sky glow from Ottawa. But here's M1, the Crab Nebula. Quite an interesting supernova remnant. You can see a lot of the filamentary kind of outline on this and the dark shadow at the bottom, which makes it look a little bit like a crab's claw. This is a stack of 86 30-second exposures with my 73 millimeter telescope and the ASI 178 MC camera. Next one. And with similar viewing conditions on the same night, this is M78 in Orion. It's just above and to the left of Orion's belt. And I think it's very amusing. This one is sometimes called the Casper the Friendly Ghost Nebula. Now, you may be able to see just above Casper is a kind of dark band. There's a lot of dark nebula around in this area, but it's very difficult to pull it out from the Ottawa sky. So the next clear night, I went out to FLO, next line, and tried to get some dark nebula. Here's the Horsehead Nebula, probably my best picture so far. And I had so many difficulties before with the bright belt star off to the left there that I deliberately aimed my camera just at the Horsehead, didn't try to get the star, didn't try to get the Flame Nebula nearby. And I think that worked out pretty well. I could still do with longer exposures, still working on it, always. Next one, please. And you may remember that I showed a mosaic of the Orion Nebula as part of my presentation earlier. When I was out at FLO, I decided to extend that two-panel mosaic to another 2 panels to include the Running Man Nebula just to the north of M42. So I'm pretty happy with this field of view now. This is probably about 3 times as big as the camera, but I made it out of 4 panels, so there's some overlapping. And using the plate solving technique of removing the distortions from the individual frames, I don't think you can see any joints between the frames of this mosaic. So I'm very pleased with how this technique is working out for me. Okay, that's all for me.
Okay, thank you, Richard. Jim, Sophia, you're up.
Thank you. Well, some time ago, I was imaging Mars, and the seeing was good that night. When I was done, I decided to check out the moon, which was slightly beyond the first quarter phase. And this is one of my favorite times to see lunar features, especially along the terminator. After looking at the moon through the eyepiece, I was really very impressed. So I decided to mount my cell phone to an adapter and attach it to the eyepiece. Now, I know that this idea was mentioned before in previous meetings, but I'm going to promote it again. This was my first shot, straight from the camera, no post-processing at all. Next one, please. And here is the simple setup. The phone is attached to an adapter, which stabilizes and centers the phone camera to the eyepiece for a full telescopic view. Trying to do this without the adapter would be pretty messy. The adapter really stabilizes and makes this process very easy. And there are various phone adapters on the market for this purpose. Next one, please. And here is another image taken. You don't need a large aperture telescope to do this. The moon is bright, and if the seeing is good, it's going to turn out well. These shots were taken with my 8-inch scope and a UV IR cut filter, which can improve the contrast. So if you're interested in learning about lunar features, this is one way to start your own library of lunar photos. Next one, please. And here is another area of the moon showing the crater Plato at the top. Next one, please. You can zoom in to an area of interest, just like I'm doing right now. And this particular image was the only one that was post-processed to enhance the sharpness and detail of the mountainous regions. Thank you.
Thank you, Jim. So we're going to turn it over to Bob Olson.
How do you do? This globular cluster is found in Aquarius, which means you have to see it in the dusk now. It's almost visible naked eye. It's 55,000 light years away and contains about 150,000 stars. Next picture, please. This is my M78. It's just above Orion's belt, as somebody mentioned. It's 1,350 light years away. It's a reflection nebula, which the blue color is because blue light is preferentially reflected off of dust. It's an area of young stars just being formed. To me, as I mentioned earlier, it's a ghost, they sometimes call it the ghost nebula. Or Casper Nebula, but it really looks spooky to me. Has a real spooky look to it. Next, please. This is 108. It's found at the bottom of the Big Dipper, in the Dipper. So easy to find. It's sometimes called the surfboard galaxy. It's 28 million light years away. It's got 128 billion stars. The black hole in the center of it has a mass of 24 million suns. In my image, there's an awful lot of massive dust lanes showing. Fantastic. Interesting sort of side fact. I don't think I've ever looked at this through a telescope. I certainly looked in this area visually, but I don't recall seeing this galaxy. Anyway, next time out, I'll take a look. Have a great day.
Thank you, Bob. I'm going to turn it over to Oscar.
Hey, good evening, everyone. Got just a couple images to present tonight. This first one here is of the Crab Nebula, which, as was mentioned earlier, it's a supernova remnant and a pulsar wind nebula in the constellation Taurus. The moniker actually came from a drawing in 1842 by William Parsons, and his drawing looked like a crab. I'm gonna try to look for it and maybe show it at some point. And he used a 36-inch telescope at the time to observe the nebula, which is pretty amazing for 1842 to be using such a large instrument. The nebula lies about 6,500 light years away, approximate diameter of about 11 light years. At the very center of it is a neutron star that pulsates, that emits radiation from gamma rays all the way to radio waves. So we can type that from here. So this image I took with the 11-inch GHD using a ZWO ASI 2400 MC Pro camera on the nights of the 30th of September, October 3rd, and October 23rd this past fall. So it's made up of 104 3-minute sub-exposures for a total integration of 5 hours and 12 minutes. Next one, please. All right, so this is Melot 15, the very center of the Heart Nebula. So it has it's made up of some really beautiful cosmic cloud formations. You can see the bright nebulae in the middle, which are all hydrogen alpha, ionized hydrogen gas. So they're emitting hydrogen alpha light. And then also some really beautiful dark nebulae there on the bottom left and along the bottom where the dust is obstructing the emissions from the surrounding nebula. So this nebula sits about 7,500 light years away, and it's in the constellation Cassiopeia. Again, this was taken with the same equipment as the previous image, so the 11-inch Edge HD through the ZWO ASI 2400 MC Pro. And this was done the nights of December 12th and 14th, which to my recollection is the very last clear nights we had. Well, I heard mention of someone imaging there in January this year, but I was away in Dominican Republic at the time, so it doesn't count. So this one is made up of 64 3-minute sub-exposures, so a total of 3 hours and 12 minutes of integration. I'm hoping we get some clear sky sometime this century, so I can do some more imaging, but we'll see. Thank you.
Okay, thank you, Oscar. I turn it over to Paul Clevenger.
Thank you, Dave. I'm just going to cut my video here, just to
Okay.
make sure that I stay smooth. Still good?
Yep, you still hear you.
Okay, great. Okay, well, good evening, everyone. We've, as a few people have mentioned, we've certainly had our challenges for both visual observing and astro imaging over the last 2 months. Certainly the cloudiest winter I can recall in quite a while. So I guess we have to take what we get in terms of sky condition, even when it's just marginally clear or with and without a moon out. Given that the universe likes to play deep sky handball sometimes, the moon can be a temporary refuge for us starved observers. And so we can take advantage of those times to explore our nearest neighbor. Last month, Oscar set the crater Vendelinus as the lunar challenge object, and this month, the crater Langrenus. Both of these targets lie close to the eastern rim of the moon, and so are only well positioned for good observations or imaging for a limited time each month, as Jim Thompson pointed out earlier with his very cool image of the same area. Interestingly, I didn't know Jim was showing that image there, but his is kind of on the opposite phase of where the sun is, as opposed to mine. This is very near the sunset for this region, and so the shadows are in an opposite direction from what you saw in Jim's. At any rate, both of the craters that Oscar identified, they're actually next door neighbors, and this is a really interesting area of the moon to explore or image. So I thought it merited a closer look. This image was taken as lunar sunset approached this area, and Mare Crisium, the Sea of Crisis on the left side, is just a wonderful target for exploration at this time. You can see that 3 days. This was taken 3 days after the. Sorry, got my wires crossed here. 3 days after full. No, I'm sorry. No, the timing on these areas that I've calculated is that they're best seen actually 3 days after the full moon and 2 days 2 days after a new moon. These provide the low shadow angles to really bring out the topography in this region. The broad lunar lava sea that is Mare Crisium is about 360 kilometers in diameter and is ringed by an impressive mountains bordering it just on the flat flooded floor of the plain. These really come out at this time in the lunar cycle, and you can use a telescope, especially if it's a clear, stable night at high resolution, to really get into this and explore the various features there. You can see it's pretty rich in detail there for those features. Our challenge object this month, Langrenus, is also an impressive deep crater at the top center, and with a much older and eroded crater, Vendelinus, just off to the right side. At the right edge of the frame is, in this area too, is a very distinctive crater Petavius with its steep terraced walls, impressive 1,700 meter high central peak, and a system of pronounced rills on the floor. This is just an awesome target for high resolution imaging or observation, especially when the sky is steady. If you get a chance, you should definitely take it in while you can there. You can spend just hours exploring this region. And the nice thing with the moon is it's never really quite the same. It's never really quite the same from one night to the other in terms of seeing it. And even if you're looking at similar phase, just a few hours can make quite a difference in the shadows here. Okay, so the next one here, please, Chris. Oops, I thought that was displayed already. Sorry. I must be behind in my video feed from you guys. Anyway, this is a slightly closer look at this area with the craters that I was just talking about. There we go. And if we can look at the close-up of Langrenus on the next slide, please, Chris. We'll zoom in a little bit here. This is the lunar challenge object for this month, and it just has some exceptional structures within this area. It's 133 kilometers in diameter, and this crater has a really sharply defined rim and steep terraced walls. You can actually see details of the terraced walls, especially in the sunlight and the shadowed regions there, where the topography really can pop out. those terraced walls are actually amazingly deep. They plunge like 2.7 kilometers down to the floor of the crater. And the floor of the crater itself is seen to be hilly on its western side, which is the lower partially shadowed side of this in this view. I've rotated the image here. And at the center of the crater lies its central peak, which you can actually see comprises two mountains that rise about 1,000 meters above the floor. You can see their shadows being cast above them onto the floor. This crater, by the way, was named after Michael Florent von Langren, who was a 17th century Belgian engineer and mathematician. Check out this feature if you get a chance, and especially the nearby Petavius. These are just super interesting objects to see on the moon, especially at this time in its phase. Okay, next one, please, Chris. All right, well, my last slide takes us a little bit further afield to Comet C 2022 E3 ZTF, a favorite of the internet at this point in time. This has been a challenging object to capture due to the extensive cloudiness we've experienced so far this winter. And the nights that have been clear have often been dogged by the moon, unfortunately. This image was taken on January the 26th, 5 days before its closest approach to Earth. And it is a stack of 12 45-second exposures using my Canon 70D with a 300 millimeter lens on a Star Adventurer mount. Excuse me. You can see three tail-like structures apparently emanating from the bright coma. The most obvious is the narrow, well-defined bluish ion tail extending from the coma to the upper right of the frame. In the same direction as the ion tail is the much broader but less well-defined parabolic-shaped dust tail. It's quite bright near the coma, but fades rapidly with increasing distance away from it. The third apparent tail extending down into the left from the coma is probably the most difficult one to image there. I had to do longer exposures to catch this one. This is referred to as the comet's anti-tail. It's actually dust that has been shed by the comet and lies in the comet's orbital plane. Now, Earth crossed the comet's orbital plane 5 days before I took this image, and if it would have been clear at that time and you'd taken the photograph like this, you would have seen that the anti-tail was in the same line as the ion tail, but still on the opposite or anti-side of the coma. So that's Comet ZTF. It is a darling of the internet at the moment, or it has been for the last little while. Not quite sure why that is for people in our area here. Maybe it's just our skies there, but people were saying how fabulous this is. It's an interesting comet, certainly photographically, but you know, I've seen it on 3 nights that were reasonably open to observations, and on one of those nights it was just barely visible to me. And I have pretty dark skies out where I live. It was just barely visible, and I knew exactly where to look. So if you've been out trying to see this thing but hadn't the charts or anything to support where to look, you were probably disappointed. There is stuff available online, things like the Sky Live and such, programs like Stellarium that will show you exactly where in the sky to look for this. But you definitely want to try it with binoculars or at least a small telescope. The view I had through binoculars was pretty reasonable, but you certainly didn't see the anti-tail, or I didn't see the anti-tail. Did see the coma as a greenish smudge, and just the faintest traces of the dust tail. So it has been challenging, but at any rate, it's there, and it is at supposedly at around magnitude 6 at this point in time. It has passed the Earth now, and it's heading on its way out, but it will start to drop in brightness very rapidly over the next couple of weeks. Unfortunately, the moon is up right now, and it will be out of the picture probably in about a week or so. So if you do want to get a chance at this, and if we do get some clear skies, that in about a week or so will be your best opportunity to do so. That's it for me this month. Wishing you all clear skies. Have a nice weekend.
Thank you, Paul. So here were the observing challenges from last month. SA 35, NGC 2174, IC 2196, and Crater Langrenus. So what are the ones for this month? A deep sky challenge for the beginners is IC 1848, known as the Sol Nebula. All of these challenges will be in Astronauts, which will be released very shortly. So I'm not going to read all the details here. They will be in Astronauts. The intermediate challenge is Apple 21, also known as the Medusa Nebula. And the advanced challenge is IC 443, also known as the Jellyfish Nebula. And our lunar challenge is Crater Petavius. So good luck with that. There's a summary of what they are. Again, these will be in Astronauts. Anybody who's a member of the RASC will receive that via email. And we invite you to visit the Fred Lawson Observatory, and we do have a members-only night scheduled for, next slide, February the 18th. Hopefully it'll be a little bit warmer than tonight, and hopefully we have clear skies. So here are some of the folks that help run our club. So you'll see that we have a new Ted Bean Equipment Loan librarian, Peter Schutz. So welcome aboard, Peter. He's just received all the equipment. He's in the process of going through it right now, and look forward to him sending out an email at some point with all his contact information and what he's got available. And we're adding to the library as well. Okay. So I think we had at one point about 69 people, plus those on YouTube and so on.
Actually, I was up to a max at one point of 79, so we probably
79,
had about 85 people attendance.
85
people tonight. Yeah.
Oh, that's super. So we will be, once we do move back to the Canadian Aviation and Space Museum, it is our goal to have these meetings hybrid, so that for those of you who've been getting very comfortable watching this online, and on a night like tonight where it's bitterly cold, you don't have to get out of your own house, we will have these available. We just have to work that out with the Aviation and Space Museum. Any ideas, please send your email to meetingchair@ottawa.rasc.ca. And videos of tonight's meeting will be posted to the fabulously put together website, and we're hoping to get Mick back as our meeting chair at some point. Right now he's under the weather, and so you've had to put up with me, former meeting chair and president. So thank you folks for coming out, and we will see you next month, Friday, March the 3rd, 7:30 p.m., same bat channel. Thank you folks. Have a good evening. Clear skies.